Once that core gets heated up, carbon starts glowing white hot. So it becomes like our sun inside that thermal battery. Then we have insulation around it so that heat does not escape out. Then we have a mechanism which is like a door. We open that door to shine that light, basically use radiation as our heat transfer mechanism to take that light out from our thermal batteries and then deliver it back to the customer in whichever way or shape or form they want. Some customers might want steam, so we just take that heat and help convert that back into steam. Some customers might want that heat directly.
Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hardware to Save a Planet is brought to you by Synapse. Make sure to click subscribe so you don't miss any future episodes. Thanks for listening. Hello and welcome to Hardware to Save a Planet. I'm excited to be speaking today with Nehali Jain. She's the Chief of Staff at Antora Energy. Antora has developed thermal batteries that store renewable electricity in the form of heat in carbon blocks. That energy can then be deployed later as either heat for industrial use or as electricity by using thermophotovoltaics. This has the potential to decarbonize heavy industry like steel, cement, and chemicals, which make up something like 25% of our total emissions. As Chief of Staff, Nehali leads fundraising and strategic growth at Antora. Early in her career, she helped shape climate strategy at the Bill and Melinda Gates Foundation. She's also been with a number of climate tech startups, including Form Energy in the battery space and Verdox and Prawn in carbon removal. And she's also been on the investor side with Mission One Capital. So I'm really excited to chat with her. Nehali, it's an honor to have you. Thanks for joining.
I'm glad to be here. Thanks for having me, Dylan.
It was fun looking through your background. It looks like you've spent the majority of your career focused on climate, if not your whole career. And you've worked at some startups that I've been watching and been interested in. So that was cool to see. I'm curious, how did you get started down that path on focusing on climate change?
I think my interest in energy goes way back, way beyond. I started even working in climate. I actually grew up in India, and my father used to work in the oil and gas sector. So I grew up in oil refineries, and my weekends would consist of going to his refinery and looking at the naphtha cracker unit. And these refineries usually are a little bit away from the city. So we used to be around 20 to 25 miles from the nearest city. There wasn't a lot to do. So I would just spend a lot of time being along with him. And I think to me, energy was fascinating from that time. It was very clear to me early on that energy really powers everything. While it's just 5 to 10% of a country's GDP, it's the first 5 to 10%. I get to do everything that I love because I have the energy backing it. So I think my interest in energy started then. I became a chemical engineer, never really used much engineering till now, but then spent time at BCG doing management consulting projects across energy, industrial goods. And I was soon realizing that the energy that used to power us 20 years back will not be the energy that powers us right now. And there was just a massive feeling inside where I was like, oh, I want to be doing something which is at the earlier stage. I want to be working on a technology that transforms how we can use energy, that transforms the way we think about costs, etc. And that's what really drove me to figuring out within the climate tech space, which are the new technologies that are up and coming and are really solving a problem that hasn't been solved. When I started doing that, I was looking at EVs, I was looking at multiple different sectors, and I soon realized that there are already so many people thinking about certain technologies and not enough people thinking about certain other technologies. That's how I landed up myself thinking about energy storage and industrial emissions in the first place. And as I was doing that research, you sort of pointed out a few names. I am a big fan of figuring out something by just doing it and trying it out, which is why I ended up working at different companies that were trying to solve this problem from different angles. I also spent some time investing in technology so I could just wrap my head around what's happening in the sector. And then finally, I came across Antora and the founders. And hearing their story, it felt like they did the exact same thing as I did, which is really take a spreadsheet and draw out what are the biggest problems that are facing us, what are the technologies that can solve them, which technology can have the biggest impact in the shortest amount of time possible.
Why is it that this particular solution is so impactful relative to all the other things you could be doing?
Yeah, I think the fundamentals of it, the fact that on day one, we decided that we want to build a technology that can beat the existing technology, which might be based on natural gas or coal on cost. We don't want to be building a technology which will take 20 years to get deployed. We want to work on a solution which can be cost effective from day one. I think when you go to the market with a thinking like that, you try to optimize a lot of different pieces and you make certain decisions a certain way. So for example, and I will walk through why we have certain elements in our batteries a certain way. So for example, the core of our battery is carbon. Now, carbon is extremely abundant. It is the fourth most produced man-made material on Earth after steel, cement, and aluminum. So the fact that it is so abundant also makes it really cheap, also makes it really safe because it's been used in the industries for as long as we know. It's used in steel making, it's used in the aluminum industry, and so on and so forth. So that being the building block of this technology could just show me that from day one, we can create a product which just can go to market and tell customers a story where they don't really have to think through, hey, do we want to pay a green premium for this or not? They just need to make the decision that, okay, this is an alternative.
Right. Relative to like an electrochemical battery that has rare earth metals or something that isn't quite as abundant and might have other costs to extract.
Yeah. So I think for me, that was the first thing, which is our technology is extremely solid. It is not using any elements which are scarce. So it's using cheap, abundant materials. It's extremely safe. And then the people that are doing this work are people that are extremely nice humans. And I think that is what I stuck to. And yeah, these are all people who are extremely passionate. I've been with the company for 2 years now. And I can say that every morning when I wake up, I'm like, oh, I want to go to work and I want to get started as soon as possible. And trust me, I've been working for the past decade. This has not happened before.
Okay.
Yeah.
And what about like zooming out, even just sort of the challenge of energy storage as being one to focus on? There's energy generation and there's electrification and there's carbon removal and all these other places. And you've spent some time in some of those areas. Agriculture, I think I saw when you were at the Gates Foundation, some of your work was focused on maybe agriculture and land use. Like
that's right.
These are all other big problems. Like why, aside from the specific aspects of the Antora solution you mentioned, why energy storage specifically? Why is that something that really draws you?
Yeah, absolutely. So I think just reflection on where we are today. Today, we're living in a world where the cheapest form of primary energy, for many hours in a day, is solar and wind. Just point blank. That is the cheapest form of energy. But then, while it is the cheapest, many of us cannot use it because it's intermittent. Solar energy, the sun only shines a few hours a day, the wind only blows a few hours a day. So while that phenomena exists, we're unable to tap onto it. And that to me was a big gap. And I really get attracted to whenever there's a big gap. That is exactly why I'm in this role, chief of staff, where my whole job is to identify gaps in the organization and fill them. But in the broader energy space, you have this big problem of intermittency, which is that industries want to use a lot of energy. They want to use a lot of heat. They want to use a lot of electricity. They are unable to tap onto solar and wind because of this intermittency. And the only way to solve that is storage. You need to find a way to store it. Now, there are so many different solutions that exist in the market for storage. You have lithium-ion batteries. You have so many different kinds of batteries. And when we started, we did not start with a technology in mind. Antora was not built to commercialize thermal batteries. We started with the fact that we want to solve energy storage as a problem. And then we looked at the whole solution space. We looked at electrochemical batteries. We looked at hydrogen. We looked at thermal batteries. We really scoped the entire space and figured out that the most cost-effective way to do this is thermal energy storage. And especially when you focus on heat, which is about 2/3 of the entire industrial emissions, the cheapest way to solve that problem is through thermal storage. And that's exactly why storage sort of piqued my interest and Antora's interest.
Yeah. And is your approach specifically about addressing the challenges of these heavy industries, cement and steel and chemicals, or is it really kind of grid scale energy storage that will provide, even out this intermittency to anybody plugged into the grid? Or is there something specific about it that makes it directly applicable to the industrial applications? I suppose providing heat, direct heat, is one reason.
Absolutely. We, as you mentioned, our product, the core product, stores energy in form of heat. Now we can supply this heat back to customers in two forms. We can either supply the heat back directly, or we can convert it back into electricity and supply both heat and electricity together. For us, we can do all of these. Just the heat mark in itself is so huge. This was the market feedback that we got from our customers. We went to them saying that, hey, we have these two products and the TPV technology is also an amazing technology there. We've demonstrated north of 40% efficiencies for heat to electricity conversion, which are almost unheard of. These are extremely high efficiencies. And especially when you combine that with our heat product, which has an efficiency north of 90%, whatever heat is not converted into electricity can actually be sent back as heat. So the overall system efficiencies are still extremely high, north of 85% or so. Our customers were like, that's great, Nehali. But, why don't you just solve heat for now? We have such a huge need for heat. Why don't we start there? And we started hearing this not just from one customer, from 40 customers back to back. And that really made us go back to the drawing board and think about our plan. And that's how we decided that the first product that we will go to market with will be the heat-only product, which we are calling the heat core product, which can provide steam up to 400 degrees Celsius. And then the next product is the combined heat and power product, which uses the thermophotovoltaic technology. And the third product is the high temperature heat product, which can provide heat up to 1500 degrees Celsius. And I think across the spectrum, the market is just so huge. And I can keep on talking about how each of these three products are extremely differentiated and tap on a really big market by themselves.
And I suppose the heat-only product is also probably simplest from a system engineering standpoint, so a good one to start with.
That is absolutely right.
And does it then sit sort of behind the meter at your customers' facilities rather than something that's on the grid operated by utilities, I guess, if it's providing
That
heat?
is right. So these are product or our batteries would be co-located with any facility, any industrial facility that requires the steam. We did this analysis where you're really deciding between, do I want to be transporting heat or steam, or do I want to be transporting electricity? It's almost always easier to transport electricity than to transport steam. So that is how we decided to be co-located with the industrial facility.
Right. Bring the electricity to where you need the heat, and then generate and store the heat until you need it. And I guess, is it fair to compare it against batteries? You were talking about sort of like efficiency. Do you think about it in terms of like energy density relative to other battery or energy storage solutions, or cycle life or lifetime of the battery, that kind of thing, cost per levelized cost of energy? Like, how does it compare on some of these kind of key stats when people look at energy storage solutions?
So we think through all of this. But not to compare ourselves really. I think these two technologies are complementary. We think of ourselves as complementary to lithium, and right now can do anywhere between 4 to up to 8 hours of storage. That is a very different application to what we are trying to do, where we are trying to supply 24/7 heat to our customers. So it's a very different application. But the things that you mentioned are exactly the things that are on our mind. So I started talking about carbon and how we love carbon. But another reason we love carbon is because of its physical and mechanical properties. And one of that is energy density. It is extremely energy dense. It is almost 4 times as energy dense as lithium-ion batteries. And given what we're doing here in our batteries is really swinging it back and forth between temperatures as high as 2400 degrees Celsius to the temperature that the industrial customer really requires that heat. We need a material that can keep on swinging and that can store that energy. And carbon is by far the only material out there, even within the thermal energy storage landscape, that can go to temperatures as high as 2400 degrees Celsius. And again, this is nothing new. Electric arc furnaces use carbon electrodes, and they use carbon electrodes at temperatures as high as 2700 degrees Celsius. And they literally have an arc passing by, and they put all the steel slag, and the heat makes the steel melt. So they use it for purposes which are much more extreme than we use it for. But then carbon is extremely energy dense. And to your point, that's one of the reasons we use it. There are many other reasons. For example, it has extremely high thermal conductivity, which makes sure that the heat gets transferred to the entire block instead of staying local. And that's important for us because the more easily it gets dispersed within the block, the more the capacity we can get. Yeah. So we think a lot about energy density, and that is one to make sure that we're able to store a lot of heat in our batteries. But then there are other implications of energy density, such as cost. So if you have high energy density, you can use smaller amount of material, which definitely takes the cost down. Second, any balance of plant also gets sized based on how big your unit is. So if the unit is smaller, then rest of the cost that goes into piping and everything else that goes around your batteries also becomes smaller. And that really helps reduce the overall installed cost. And then finally, if everything is smaller, then you need lesser space. And that's always very helpful.
Right. You can fit in a smaller footprint. You need less land.
Absolutely.
Yeah.
Absolutely. Actually, one more thing that I missed talking about is that with these properties, you can also make your battery modular, which means that you can just build them in a factory and ship them. If it's a very big installation, you'll have to do it custom at site. And we very early on, we realized that is not something we want to be doing because it is not scalable. So all our modules are modular, and it's basically repeating blocks of one unit. And that also gets the cost down. So if you have a modular product, you can just build multiple of them that are efficiencies of scale and so on and so forth. And that can really get your cost down. And we are just starting to realize all of those savings. And we're like, oh my God, that's such a good decision we made.
That was a good move.
Yeah.
It's so funny. That theme comes up in so many of my conversations, that you want to build, if you really want to come down the cost curve and progress through all these sort of iterations of learning and product design maturity and stuff, that build lots of small things rather than a few large installations. So it sounds like you nailed that. How big is a module? Is it like a shipping container? Would be
Half
one
a
module,
shipping container is
Okay.
one module.
You talk about, I think, what'd you say, 2400 degrees Celsius, the carbon is heated to? So that's like really crazy hot. I've never worked on anything that gets to that temperature. I think the melting temperature of steel is like 1800 or something. It's anyway, that's really hot. I'm just curious, getting into the kind of engineering aspects of what you're doing or the sort of physical implementation of this. Can you describe what the main building blocks of the system are? And then I'm curious how you handle something at that temperature within a system like that, and how you insulate for it so you can store all this energy for as long as you do and that kind of thing.
Yeah, absolutely. So the way our system works is that we take in electricity. It can be from any source. It can be solar, wind. We're agnostic. It can also be nuclear, hydroelectric, whichever. But for now, we're focusing on solar and wind. So we take in that electricity. Then the system is resistively heated. So you think of a giant toaster, like your toaster converts electricity into heat. We have resistive heaters that convert that electricity into heat. That heat gets absorbed by the carbon core, which is at the center. And like you mentioned, 2400 degrees Celsius, it's extremely hot. But that temperature really allows us to service any temperature process. So for example, if you're working in steel or cement or trying to heat a process that requires heat at 1500 degrees Celsius, if you're storing heat at 1500 degrees Celsius, there is no delta T. So you won't be able to service that process. So only when you store at higher temperature, that is the delta T that you can thermodynamically leverage to do that work. So I think that's why it's very important for us to be storing heat at as high temperatures as possible. Once that core gets heated up, carbon starts glowing white hot. So it becomes like our sun inside that thermal battery. Then we have insulation around it so that heat does not escape out. Then we have a mechanism which is like a door. We open that door to shine that light, basically use radiation as our heat transfer mechanism to take that light out from our thermal batteries and then deliver it back to the customer in whichever way or shape or form they want. Some customers might want steam, so we just take that heat and help convert that back into steam. Some customers might want that heat directly, so we just use radiation and shine that light directly on the product that they want to be heating up. And some customers might want electricity, which is when we put our thermophotovoltaic panels right in front of that. And those panels serve as the very similar process to what solar PVs do with the sun. For us, the sun is this carbon block, and they convert that heat back into electricity.
So it's like a tanning bed. Maybe a terrible analogy, but interesting. Okay. So your customer actually places these directly where they need the heat. Do you do the receiving? Do you help them with the sort of, how do you receive that thermal energy and how do you convert it to steam, or is that kind of up to them?
So for steam, we're taking care of all of that. What the customer gets is, instead of the steam that they used to get from their natural gas boilers, they would just get it from our system. But we take care of all of the balance of plant for them. There is nothing they need to be worrying about. The final product they get is steam.
Or electricity. Are the thermal photovoltaics, is that something proprietary to Antora, or is that a known technology you can kind of buy and leverage?
Both. So the techniques that we have developed in the exact materials that we use within our TPVs, that is something that's proprietary. The technology has existed for a long time. In fact, this came up for us because one of our advisors, Dick Swanson, who is the founder of Sun Power, he worked on this technology in the 1970s. And then at that point, nothing much came out of it. And he told us that, hey, maybe now is a good time to really think back on that and start progressing it a little more. So we really took the technology or the work that existed, started using more thinking around, how should we design the system? And eventually our team was able to get the efficiencies up significantly, and which is why now it makes all the more sense. And I think a core building block of TPV technology is that you should be able to take in the electricity that you're taking in a cheap fashion so that it all makes sense. And that is only true now. So while the technology has existed for a long time, the application and the design of the cells to make sure that we're getting maximum efficiency, that is something that Antora has sort of worked on over the past few years.
What has been, from an engineering standpoint, what has been challenging about making the system work and getting it to where it is today?
I think the challenging thing has been just doing a lot of iterations to make sure that the system is simple and the system is meeting the cost targets that we want it to meet. So there has been just a lot of iteration on that. And there were times when we were working on things which were great in the moment, but they would make the system more complicated. And we decided not to do that. So for example, even the way you take out heat, traditionally, a lot of people think of using fluids, so using air to take out that heat. We decided not to do that because that introduces a lot of complexities. While it would be great to do that in the short term, over the long term game, it will just make it difficult for us to scale in the way that we want.
As opposed to radiation, the way you described.
Yes.
Yeah. You could blow air through your carbon blocks or something like that to transfer the heat out, but you're doing it with radiation. Is that what you mean? Yeah. Which I guess must translate to like the form factor of your batteries. You want to have like all the surface area of the carbon blocks exposed when you open your door, right? To get as much radiation as possible.
Not really. That's a great question, though. That was my question as well when I was thinking about it. You don't need all of the carbon blocks to be exposed. You just need the right amount to be exposed, and you can optimize that. So we've optimized the system based on what is the power that the customer really needs, or how much power do we want one module to be outputting? And the rest of it just stays in. So really, it's a mathematical function where you want to optimize for how many hours of storage, how much output power do you need, all of that. And, essentially with how much charging do you want to be at, how fast do you want to be charging your system. So these are sort of the parameters to think about. And for us, we've been able to optimize the amount of storage. We've also been able to optimize how fast we want to charge and discharge our systems. And right now, for the first product, we can charge 3 times as fast as discharging it, which means if you want to be supplying 24/7 heat or power, to be able to supply it for 24 hours, we only need to charge for 8 hours. And all of this also it is not as if you're charging and then discharging. This keeps on happening simultaneously. And that really allows us to grab the lowest cost 8 hours of electricity.
That makes sense, because I've read that even at times energy is essentially, or electricity can be free or even negative cost, right? And so you're trying to take as much advantage of that.
I will not stop talking about this. It just makes me, it's hard to fathom how even now, if I talk about US Midwest, about 10% of the wind that is generated is curtailed, which is about 10 terawatt hours of electricity, which is equivalent to usage of 1 million homes in the US. So that amount of energy is just getting wasted, and we don't have many technologies that can make use of that. So that's why we started thinking about.
Right. That's a very clear opportunity for energy storage.
Absolutely.
Yeah. And then as you scale, where are you at in the process now? How many systems have you built, or how mature is the system? Do you have pilot customers already, that kind of thing?
We started serial production in the facility that I'm setting out of late last year. Before that, in 2023, we deployed our first pilot that's been running for about 2 years now, and that's been working great. That really gave our first customers the confidence to be signing 20-year offtake contracts, where right now we're doing construction and developing that first commercial project, and that will go online later this year. So we're already churning units out of this manufacturing facility, which it is a multi-gigawatt hour facility, and that's our first one. So super excited for everything that's in store for this year.
My question was going to be, as you scale to higher and higher volumes, because I imagine you need to have the sort of impact you want to have eventually, there's lots and lots of these modules, these half shipping container-sized modules you want to build. What do you expect some of the challenges to be as you scale? Are there supply chain challenges? I mean, carbon's clearly very abundant. Are there other supply chain issues you might run into, or design for manufacturer? Or what is it that kind of keeps you up at night when you think about that, the kind of scale you want to do?
I think what keeps me up at night right now is just execution. How do we deliver on these commitments that we have? And the reason I say that, you mentioned supply chain, I think our supply chain team has done a great job at making sure that we have multiple suppliers and from multiple geographies for each and every element of our supply chain. And that really served us supremely well right now. All our manufacturing is happening here in the US, right in our factory. So we're not concerned about what will happen to our manufacturing, because we're doing it all in-house here right next to us. So that is not a concern for me right now. I think for me, the concern is how do we execute on the projects that we have? And secondly, how can we keep sourcing this cheap power over and over again? And that really means working in different geography. You're always starting from square one because you're working with a different utility and you're working with a different co-op. So how do you make sure that we create a model that is extremely scalable, replicable, and do it not just in one geographies, in all different geographies here in the US and then even outside of the country.
So I was going to ask about your business model. Are you procuring the power and supplying heat as a service or steam as a service or whatever it is to your customers? So it's up to you to go and make sure you're doing the power purchase agreements and operating and maintaining your thermal batteries and everything, and your customers just have this kind of service agreement.
Yeah, so the way we're developing our projects here right now are we do heat as a service for our customer. So our customer signs an offtake for heat as a service. And basically, that's one partner in this entire equation. Then we have a project company that we sort of might be part owners with some external financiers who goes on and builds the project. So it's a project company that's formed. We might be equity owners in that project company. We also get external financing, project financing for that project company. And that project company really goes about, takes batteries from Antora and builds the project. So it's essentially that project company securing the PPAs with the utilities or wholesale power prices and forging those contracts. Given we're heavily involved right now, and in the first few projects, we, I think, made the conscious choice that we want to be heavily involved so we get the learning cycles out of them. We are the ones who are doing all of that for the project.
But that might change over time.
That might change over time. And I think that will also, the business model will vary by geography. We might do a lot of this. We might decide to just sell our modules in a different geography where we don't have the skills and expertise. In US, I think we have a super strong team, super strong power supply team, super strong team of project developers right now that can execute well. But maybe if in a different geography, we might change that model. But this is a question that we think about a lot.
Okay, interesting. Will utilities also be like, will you have on the grid batteries at some point too, do you think? Or is it always kind of this site specific for industrial customers?
I think we can do that, but I think for the next few years, we're just focused on perfecting this. Yeah, there's such a huge market that I'll be very happy if we were able to serve this market, at least in the next years.
Yeah. When you think about kind of the future of the company or the kind of impact you can have, can you quantify that in terms of like gigatons of CO2 mitigated? How do you look at like sort of what kind of impact Antora can have and what sort of time scale does that happen over?
Yeah, absolutely. Gigatons, I think when someone starts thinking
that's a big
about
number.
Yeah. That's a big number. And I think that is the number that we're gunning for in the next 10 to 12 years.
Okay.
Yeah, that is what we're sort of working backwards from. And I think that really helps us ground us whenever we're thinking that, hey, all of this is great. Is it enough? And that's how we sort of check ourselves. Maybe it is enough. Maybe sometimes we have to push ourselves more. This is not enough. We need to be doing more. Yeah.
And that can come from converting these heavy industrial customers from fossil fuel derived heat to electricity derived heat in your thermal batteries. That kind of impact.
That kind of impact and just enabling them to be accessing energy sources that they haven't been able to so far and making sure that they are able to run their operations for 24/7. I think that is also a big driver for us. Yeah.
Cool. That's a big deal.
Yeah. Super excited. That's what sort of pumps us up every morning.
I have 3 questions that I ask everybody at the end of each episode. The first is, how optimistic or pessimistic are you about the future of the planet and why?
As if you can't tell by now, I am supremely optimistic. And I think I'm way more optimistic than I used to be 6 years back when I was only thinking about what the planet will be and not doing much about it. I think as you start getting deep in, you see these pockets of optimism and being able to work on one of those solutions that will define how we look like in 10 years, I think that really makes me super optimistic. So I'm a 10 on 10 on optimism right now.
I love it.
Yeah. And I think it's very helpful for my dad to also be a part of this industry for such a long time. And our conversations of how the human race has really evolved, and the way we're changing the things that we're doing, the way the energy mix is evolving. It used to take 100 years before, then it took 50 years for the next innovation to happen, and then it took 30 years, and now it'll take 5 years. So I'm big on camp if we can get better at how we produce electricity and energy and heat, and we can do it cheaper than we used to 10 years back. So that makes me really optimistic that these are not solutions which are just far-fetched and are not market-driven. These will all be solutions that are market-driven.
I thought about asking earlier how your dad feels about this and what you're working on coming from the oil and gas industry. And you just mentioned it. It sounds like he's supportive.
He is extremely proud. He, in fact, was the one who encouraged me to take the plunge because he's seen in his life cycle, and he spent 45 years of his career at the same company. So he's seen how that company sort of evolved, and the technologies that they were working on are now technologies that are powering how we move around, how we consume. So he's very excited. And now I'm doing the same things that he used to. So last week I was at Setup Week, and he's like, oh, for the longest time in my life, I used to be the one who would go there. It's, full circles.
That's awesome. Who is another company or individual doing something to address climate change that's inspiring you?
So many, Dylan, to be honest. There is so much inspiration, and people are working on technologies within the energy storage world, carbon capture world, geothermal, and there's a new technology coming out every day. I think so many. One top of mind right now is Forvo. I think they're doing a great job, very inspirational in terms of the partnerships that they're forging and how they're making different players of the puzzle think about a solution in total. I think they have a good technology and excited for what they're doing.
Yeah, I've been watching them as well. They seem really exciting. That's Tim Latimer, right?
That's right, Tim.
What advice do you have for someone not working in climate today who wants to do something to help?
Just work in climate. Just reach out. I would say that many of my conversations in climate started with a cold email, including this one. That first conversation that I just could not get out of my head was through a cold reach out. So I would say if you're feeling inspired by someone, just reach out. I found that to be a barrier for me for a long time. So I want to put it out there in the world. And especially people who are working in energy and climate, you will see that they are eager to support more and more people coming into the space. So I would say,
Totally.
Stop thinking, start doing.
Yeah, I've found that as well. People seem like so collaborative and welcoming, and so many people in this space are coming from other industries that there's a lot of kind of understanding of that. And yeah, I found that too. That's awesome. Okay, well, that was really fun. Thanks a lot for your time. I appreciate it.
Likewise, great to be on the show.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.